Hello, everyone who is presented here. We start our conference for young scientists in computational science, and before we start, I would like to give a word to the director of the School of Translational Information Technologies, Professor Alexander Bukhanovsky.
Dear colleagues, let me open our annual event, our Young Scientist Conference in Computational Science. This event has an 11-year history because at least not 11, 12 years ago, we together with Professor Peter Slot from Amsterdam University decided to create the conference especially for young scientists from developing and countries and I may say developing universities. You know, there are a lot of some universities were in 12 years ago. And initially, we planned this event especially as networking event. But now, we have some drift of our interest. Because this is not the event for developing countries or developing universities. Because last 10 years in Russia, you know, there is a high drift of the universities to the up level of education and science. So this event is also for young scientists, but namely for young scientists who want to translate his result to hard science. So this is a conference for adult science. And I hope this target, this motivation allow us to compose together the keynotes which allow you to have some motivation and some vision of the frontiers in computational science in the different areas. Also, you have possibility to present your personal results in a hard discussion, I hope. And the third part of our conference is a school not for training in some activities in some software. This is a school for training your ability to prepare good proposals for grants, for projects in area of computational science, artificial intelligence, and machine learning. So I want to wish you a good time in this event. I believe you will have a happy and some words in Russian, дорогие коллеги. Я понимаю, что говорить с русскоязычной аудиторией по-английски это такое легкое издевательство, но у нас есть коллеги, которые по-русски не говорят, и в Zoom их очень много. Много, да? Ну, не очень, но много, да, вот видишь, кивает. Вот. И, к сожалению, они не могут приехать к нам вживую, но так или иначе у нас мероприятие международное 11 лет, ну не будем же мы на 11-й год все портить и переходить на родной и могучий. Но так или иначе, для любителей родного и могучего, коллеги, мы вас тут 5 дней будем кормить, поить, слушать и немножко любить. А те, кто хочет особой любви, пусть приходят к нам на школу. У нас первое мероприятие в 15:30 сегодня. Будем с вами учиться готовить заявки на научные проекты, которые нужны для того, чтобы согреться, а для того, чтобы все-таки выиграть. Вот, и думаю, что это всем актуально, а тем, кто не понимает, зачем это нужно, я расскажу на моем вводном занятии. Потому до встречи, большое вам спасибо.
Dear colleagues, I would like to introduce first presenter, first speaker from Moscow Institute of Physics and Technologies, Alexander Gastnikov with with following lecture, gradient-free optimization for non-smooth saddle point problems and adversarial noise. And so I would like to offer following timing, approximately 30 minutes for the lecture and for questions, 10 minutes. Let's start, please.
Okay. First of all, I would like to thank the organizer for kindly invitation. This is my first experience to make a talk at Mo University. Very nice place, in my opinion. Today I plan to talk about gradient-free methods. This is very popular direction in modern optimization, for example, in reinforcement learning. Many problems at the end can be considered as gradient-free problem. Anyway, this problem strongly motivated by arbitrary applications where we have so-called black box. But we will talk not only about gradient-free methods. We will talk about gradient-free methods for stochastic optimization problems. This is a little bit more general setup, and stochastic optimization problems lie in the core of modern machine learning. Almost any machine learning problem at the end can be considered as optimization problem of learning or education. We should choose proper weights of neural networks or something like this. And sometimes it is impossible to calculate gradient of target function. It depends on different aspects. For example, I just mentioned here one bright example. Assume you should minimize non-convex function. This function looks like, as you may see in this picture. And let us imagine that we have convex function. And this non-convex function is something small around this convex function. Let us write a tube with small diameter, and we write arbitrary function, non-convex. And if you would like to solve this problem by using gradient methods, it is obvious that you will have troubles. Just look at this function. A gradient at any point doesn't give you any useful information. For example, there are a lot of points where gradient is 0. So gradient is 0, it means that the function has an extremum. That is a candidate to be a local minima, to be a minima. And this is exponentially difficult problem to find the proper minima. If we consider this problem to be convex optimization problem with an exact black box oracle, I mean, after black box oracle, I mean that we ask at any point some oracle to return function value, and this oracle return not true function value, but it return red function value. We can consider this value as a noisy value of true function, of blue function. We would like to find the minimum of blue function. Of red one, it's not important, but for blue function it is possible to develop a effective algorithm to find its minimum, but for red function it is impossible. It's a very bad function. So I would like to say that sometimes even if you have gradient, you have possibility to calculate gradient. This gradient is not useful. It is proper to use only the function value, maybe noisy function value. And so the question is, what is the complexity of convex optimization problem? To obtain some results, I should constrain the class of function where in consideration. So I restrict myself only by considering convex function. Moreover, today I will consider non-smooth function for generality. It's rather general class, non-smooth function, convex. for example, support vector machine at the end required to solve non-convex, non-smooth problem. That is, the problem is convex but not smooth. So we will consider convex but non-smooth class of problems. Okay, and let us introduce some accurate definitions. So we consider convex optimization problem, that is target function. Target function f of x is convex. Let us mention that it is not necessarily that f of x xi is convex. Xi is random variable. Mathematical expectation is taken on xi. Function f xi is available via black box. The objective function, unfortunately, is noisy, and derivative information is unavailable or too expensive. Let me make one more remark about typical situation. In typical situation, when you have a so-called calculation tree, if you have some program that allows you to calculate function value, it is it has almost the same expensive to calculate a gradient of this function. It's the procedure called automatic differentiation or back propagation if we consider neural networks. Let me repeat. If you have some program, you write on Python, say, some program, and this program works sometime t, capital O of t. It means that the program required, say, capital O of t arithmetic operation. So you can prove that in rather general circumstance, you can correct properly this program in Python that allows you to calculate it gradient of this function, not the value of function. But the complexity will be 4t, not t. 4 times more expensive procedure, but it's not a problem. It's in capital O terminology, it is the same complexity. But it is possible if you have a concrete program, say neural network, and this program is available to you. For example, when we collaborate with Yandex, and Yandex asked us to help them educate PageRank model, and this model used some, how to say, some secrets. Where Yandex have some secrets, and for us it was unavailable to look inside this program. It's just a black box for us. This is one more example. Okay, it's just how to say, to be honest, I must say that in many situations, if you have function value, you also have gradient, but this is not all the situation. Okay, and let us formulate the main question, the main problem. So we have a noisy observation. We try to solve the problem of stochastic optimization, but the gradient of this function and also gradient of this function is unavailable. But we try to solve this problem. Moreover, we obtain so-called realization of this function with noise. That is, instead of real function realization f of x xi, we obtain realization f of x xi with some noise that has adversarial nature in general. Adversarial nature means that this noise can be, how to say, it may spoil your algorithm as much as it possible. And the only thing we fix is the level of this noise. To obtain some interesting results, we require to bound this noise with some small constant. For example, this noise can be a machine accuracy, or something like this. It's not necessarily the real adversarial noise. It can be just accuracy of calculation. Okay, and what is the state of the art results for the beginning of this year, 2022? The state of the art results was as follows. Sorry, this is this year. state-of-the-art results was as follows. If you consider stochastic optimization problem, that is, you should solve, let me rewrite the problem. You should solve stochastic convex optimization problem with oracle that return function f of x psi plus some noise that depend on current point and noise and stochastic noise. This is not stochastic noise, adversarial noise. And we say that the level of this noise is bounded in absolute value by some constant capital delta. So, and the problem formulation is, what is the oracle complexity of this problem? That is, how many times I should ask Oracle to return this value to obtain, to solve this problem with accuracy epsilon. That is, this is convex problem, convex. When I say convex problem, it means that the function is such that for two arbitrary points, when I write a line segment, this line segment lies higher, not lower than the corresponding fragment of graph of this function. This is a convex function. So I consider convex function, not necessarily smooth function. For example, this function is convex but non-smooth. We have gradient from the left side and from the right side, but not a gradient at this point. This is, say, absolute value of x. Such a function is not smooth, but it is convex function. Okay, we consider such class of function, and we ask what is the best algorithm that requires the smallest number of oracle calls to solve this problem with accuracy epsilon. That is, we would like to find algorithm that allows us to find some x bar n minus f x star. X star is the optimal value of target function. This is sorry. Unfortunately, you don't see, or you see. Colleagues in Zoom see. Okay, great. So with accuracy epsilon, so this is our goal, our purpose, to find such point x bar n that is epsilon solution in terms of function value. But what is n? N is a number of iteration or oracle calls. N is a number of oracle calls. Number of iterations. And what is the best bound, the smallest bound of n? The answer is n is proportional. Let me skip some details. Proportional to d. D is a dimension. D is a dimension of vector x divided by epsilon square. So this is an improvable result. It was proven in late 70s by Arkady Nemirovsky. So you cannot obtain something better than this result. In case when the level of noise is zero, if you consider ideal, absolute exact situation without any noise of adversarial nature, you can obtain that the oracle complexity is d divided by epsilon square. So this is the oracle complexity. And the next question you may ask, what is the level of noise? What is the level of this noise that save this bound? How much can be the level of this noise if I put this noise into the function value in realization? Algorithm will work with not exact information. And how much level of noise is available? The answer is it was obtained in February of this year. The answer is epsilon square divided by square root of d. This is the maximum level of noise. And what is interesting? What is interesting in this result? It has proven that this result is unimprovable for arbitrary algorithm. That is, if you would like to solve the problem, this problem, And you would like to solve this problem to find, that is, you consider a function, not stochastic, just deterministic, without any stochasticity. Even for this situation, you consider a convex function, you consider noise, the level of noise is delta, and you would like to solve this problem, to minimize blue function with accuracy epsilon. It is obvious that you cannot minimize blue function with accuracy epsilon that's smaller than delta. It is obvious, because delta is a level of noise, and it is in principle impossible to answer if this point is the better than this point if the distance between these 2 points greater than delta. You can compare two numbers in arithmetic that allows you to work only with accuracy delta. So it is obvious that this delta cannot be larger than epsilon. But I put here epsilon squared divided by square root of d. This is worse, much worse than epsilon. This is a bad result. This is not bad result. You may consider this result to be bad, but this is not bad result. This is optimal result. And the reason is, okay, in principle, you can find, if you have oracle that return you delta value of function, in principle, if you have too many oracle calls, you can find a real minimum with accuracy delta proportional to epsilon. It's possible. But the problem is you require exponential number of oracle calls. If you allow to fulfill exponential number of oracle calls, you can reduce this quantity to epsilon. But it's not practical algorithm. If I required exponential number of oracle calls, exponential I mean not d divided by epsilon square, but exp in the power d and exp in the power 1 over epsilon. This is or at least one of this indicator. It's too bad dependence. In this class of algorithms that allows bad dependence, it's possible to reduce. But if you consider so-called polynomial algorithm, that is the complexity of this problem in terms of oracle calls, gradient-free oracle calls, is polynomial on D and polynomial on 1 over epsilon. It is impossible to improve this bound. It was proved in 2016 at some paper at Neil Rips, Rizhevsky, I don't remember exact author surnames. I have a reference in my presentation. Okay, and it was an open problem how to develop an algorithm, such that this algorithm much lower bound. Lower bound for big class of for large class of problems. And I was wonder when I first time understand with my colleagues that the best algorithm in terms of oracle calls at the same time is the best algorithm in terms of inexactness. Just think about this, because it's non-trivial. We have two criteria. The faster is algorithm, then this algorithm is not robust. And typically, the faster is algorithm, then it is sensitive to different inexactness. But here we have such a wonderful situation that the best algorithm in terms of oracle calls at the same time is the best algorithm in terms of maximum level of possible noise. It's not typical in optimization. It's really something unexpected, and I would like to pay attention to this issue because this is really how to say, not expected situation. And let me now briefly describe some details. Okay. So at this picture, you may see state-of-the-art result. So for the recent time, the best bound was Warsaw. I mean the best bound on level of noise. You may see epsilon squared divided by d, epsilon squared divided by d in the power of 3 over 2, and in our work, we obtain the optimal bound that corresponds to the lower bound with optimal oracle calls at the same time. This is rather interesting result. And okay, what is our algorithm? I have not too much time. And I guess that I skip so-called proximal setup when you consider convex optimization problems, say on unit simplex or another non-trivial sets, and consider only standard setup that is called Euclidean. So we consider projection on some set psi big. Psi big is some convex set. We consider convex optimization problem on this set psi. Just let me remind you that in general you can consider a minimization problem on some set psi, and this psi is simple in terms of Euclidean projection. So P psi is Euclidean projection of this point xk minus gamma some vector g. This is Euclidean projection. This method called subgradient descent or stochastic subgradient descent. The main question is what is g? What is function g? If g is gradient or subgradient, this is a classical subgradient algorithm. But in our setup, prox is just a projection. In our setup, unfortunately, we do not have gradient or subgradient or stochastic subgradient. We have only function value. This is a problem. If I have subgradient, I can solve this problem by using stochastic subgradient algorithm. This algorithm is well known. Let me just show you. This is the algorithm. It's just a projection, and algorithm is xk plus 1 new point calculated as a projection of this vector. This line is nothing more as this line, because we consider only Euclidean setup. Just for simplicity, I write it down here. Записал правда на века. Я понял. I hope you can see what I have just written here. This is okay. This is stochastic gradient descent. It's не мой день сегодня. Значит, this is stochastic gradient descent. New point xk plus 1 recalculated according to the old point, current point, and corrected according to stochastic gradient. This is natural. I would like to find a minimum of function. So this is a mountain or some hill. I look into the direction of anti-gradient. This is the direction of the how to say steepest descent. The direction of what direction I have the highest velocity of descent, and anti-gradient direction is such a direction, but this is not anti-gradient. This is a stochastic anti-gradient, and it means that in average I drop down with a faster velocity, but in average, not necessarily at this realization. If I take mathematical expectation of this vector, I obtain stochastic gradient, not stochastic gradient. So if I take mathematical expectation on Xi of this guy, I obtain a gradient of this guy, and this is the direction of steepest descent of the faster direction of to drop down. Okay, and so this is the algorithm, but the problem is I do not have gradient, I do not have stochastic gradient. What should I do? And the basic idea, unfortunately, I have not too much time to describe what is Stokes theorem, Ostrogradsky-Gauss theorem. I just write two different approach how to calculate this guy. So let me remind, we do not have real value of this function, but we can calculate it this is inexact value of our function. The phi function phi is what is phi? Just let me remind you. Phi of x xi is f of x xi plus delta of x xi. So this is the Oracle call, the Oracle return. I ask Oracle, that is program, some program in Python, calculate the value of function at this point under this realization. And the program return me not exact value, it return with noise. I don't know the nature of this noise, and such a value we denote phi. So phi is such a value. Next, we consider I guess the rather obvious finite difference. So we choose at random on unit sphere vector random direction. This is a random direction, and according to this direction, we approximate derivative of target function in this direction. But look here, this is not exact derivative because we have noise. This is a derivative with some noise, and the smaller is tau, the larger is the term that corresponds to the noise. So if you would like to have good approximation, if you would like to this finite difference is close to real derivative, you should choose tau small enough. This is from one side. This is so-called bias approximation requirement. But if you would like at the same time to have a small term that corresponds to the noise, you should choose tau not small, because if tau is small, you divide delta on tau. The smaller is tau, the larger is this term. And so how to choose this tau? This is a very important question. And this is not the only variant how you can choose E. For example, you can choose how to choose approximation of stochastic gradient that can be put here. So my idea is not this is well-known idea is to replace a stochastic gradient on some model of this stochastic gradient based on a function value. Another model that based on another approximation was proposed 6 years ago and recently reopened by our French colleagues. It was L1 randomization. You choose vector not in Euclidean sphere, but in a sphere in one norm. It happens that such a randomization sometimes works better not in practice, but also not only in practice, but also in theory. This is very unexpected because many years people typically consider randomization on a unit sphere. But when I propose with my colleagues this randomization, we do not think that it is better. And when we published the paper, it was misprinted in this paper, and we obtained very, in my opinion, rather interesting result, but this result do not demonstrate that this randomization is better. But our French colleagues this year observed that randomization from this paper is really can beat sometimes classical randomization. It was, how to say, a bit we was я не знаю, как по-английски сказать, короче, мы расстроились. Потому что мы почти, в общем, сделали то, что надо. Ну ладно. Okay, let us return and let us return on English. And so our idea to replace unavailable stochastic gradient in SGD procedure by some approximation. And after proper choosing of step size, we may expect that it really works. What is intuition? What is intuition behind this construction? So the main trick is related with so-called averaging technique. So instead of real function, just let me show you here. Okay, just one moment. Okay. So you should minimize function f of x. For simplicity, let us consider deterministic setup. This is your problem, and it is the gradient of this function is unavailable. You can build finite difference, so you can build f of x plus tau e minus f of x minus tau e divided by tau, and the problem is d e. So if tau tends to zero, you can prove that mathematical expectation of this guy equals real gradient, not real gradient, derivative. Real gradient. Sorry. Yes. But just a moment. Yeah, but the problem is that for this equality to be true, you should tend t tau to 0. And this is a problem, because if you tend tau tends to 0, it is a problem with noise. I have noise. I can't tend tau to 0, because if tau tends to 0, I cannot eliminate the term with an exactness, and I have an exactness. So let us do a following trick, rather beautiful trick. Let us introduce a function f of tau x that is close enough, tau close to this function, and can be calculated as mathematical expectation of x plus tau e, where e tilde is a vector that uniformly distributed, say, in Euclidean unit sphere. So this vector e tilde is uniformly distributed on unit ball in Euclidean norm, and this function one can prove that this function is convex. It's rather smooth, and it's tau close to this function. The smaller is tau, the closer is this function to this function. And the basic idea, the basic observation is the gradient of this function, mathematical expectation of this guy, the same guy, f of x plus tau e minus f of x 2 tau minus tau e divided by 2 tau exactly equals to gradient of smooth function without any limits. This is important. I do not require to tend tau to 0. So if I put here tau, I obtain correct result without any limits. So what has happened? I say that instead of a real problem, I consider smoothed problem. I replaced function by integration on some ball around this point, and I obtained that this estimate is unbiased estimate of real gradient. Just look at this picture. This picture explains what has happened. You have function, say absolute value of x. The problem is this finite difference is not good approximation for derivative of this function, because if you consider this derivative, the derivative of function absolute value of x, it equals -1 before 0 and +1 after 0. But when you consider the finite difference, this is the slope of this curve, of this line. And you have that derivative of real function -1, here +1. But this difference is it changes continuously. So it was a big discrepancy, because this -1, but finite difference looks like something between -1 and 1. Say it can be 0, it's not a good approximation. If you have a non-smooth function like absolute value of x, it's not a good idea to approximate real derivative by finite difference. I guess it is obvious. And the idea is to introduce smooth version of this function such that if you consider finite difference, you will have exactly that this finite difference is the derivative of this function. You introduce this smooth function such that finite difference is exact derivative of this function. This is the basic idea. Okay, I have not too much time, and let me finalize the result. Okay, and next we develop some mathematics, how to converge so-called stochastic gradient descents. We based on well-known results of Arkady Nemirovsky with co-author Shapiro, Yuditsky, Lan. It was a result of 2009. And this result consider general stochastic gradient, and we have not general stochastic gradient, we have specific stochastic gradient, we have such stochastic gradient. And next we compare different approaches, this approach to stochastic gradient problem, and observed that yes, this randomization sometimes can beat this randomization, and but this is up to logarithmic factor that I skip in my presentation. That is why I do not pay too much attention to the difference of these two techniques. Okay, let me show you at the end. This is many mathematics. You may see that we estimate noise. It's, I guess, we should devote to all of this a big lecture. Unfortunately, it is difficult to describe all the details. But okay, this is two final slides. We introduced two randomization, L1 randomization on the sphere in one norm, and L2 randomization, the randomization in sphere in two norm. And I introduce also tau, the smooth parameter, the step size. And in L1 randomization, it is possible to use a larger value of tau. That is, this finite difference is more robust. It's more robust. Tau is greater. But at the end, the requirement for a level of noise are the same. So both of this algorithm with L1 randomization and L2 randomization up to logarithmic factors required the same maximum level of noise. This is our final result. And the only difference that you can observe in both of these two approaches is this factor. In L1 randomization, there is no such factor. In L2 randomization, you have such factor. This factor is appears when you consider optimization on a unit ball or something like this. Just let me interpret what is this bound about. This bound is the complexity of gradient-free methods. If you consider gradient method, not gradient free, the result will be the same, but without this factor. Because D is the payment for gradient is unavailable, and you should pay D times to estimate gradient, say by using finite difference. And many of specialists think, I guess, they think that, okay, what is gradient-free optimization? This is just let us estimate gradient by partial derivative. And since we have that oracle gradient oracle cause is one we require one oracle cause of gradient, but gradient free oracles can be approximate gradient oracle by D requests. That is, we can estimate gradient as D finite difference, and this D finite difference contain D plus 1 different values of function. So it means that gradient-free procedures D times more expensive than corresponding gradient procedures. So if we have some estimate of gradient type procedure and we would like to obtain gradient-free analog of this procedure, it is typical that the corresponding difference is D time D, I mean in terms of the desired accuracy, and it happens that in this estimate it should be D square. Yeah, this is a typical result, but it works in smooth case. We consider non-smooth case. Finite difference not necessarily approximate partial derivative. Is this first aspect. And the second aspect, just look at this term. This term corresponds to the sphere we consider. If we consider sphere in, I mean, convex optimization problem in sphere in P norm. If we consider convex optimization problem in, say, when P equals 1, it means that we consider a unit ball in one norm. It means that we have indicator 2 minus 2, because this is 1, and we have no such factor. It was a little bit wondering, because we propose gradient-free methods that doesn't depend on the dimension. And this is also unexpected, and it means that optimal gradient-free procedures is not about approximation of full gradient. This is something different. This is very also important thought. That is, it's not a proper strategy to approximate full gradient by finite differences. This is not best way. And I guess at the end, all this conclusion is, in my opinion, rather interesting, that the same algorithm is optimal in terms of oracle cause and in terms of maximal level of noise. This was unexpected, and people do not think about it. And the next conclusion is it's not a proper way to approximate full gradient by finite differences. At the end, the last slide, I would like to say that we can generalize all this result for saddle point problem, say that can appear in GAN training. We can generalize all this result in intermediate level of, how to say, of say heavy tails, in heavy tails case, and also for strongly convex or intermediate level of how to say, uniform convexity. Uniform convexity. This is if we assume that our function not only convex but uniformly convex, we may improve some result. But this is these details, I guess, not very interesting. I would like to have time for the questions. So I finish. I have finished. Thank you.
Dear Alexander, thank you. Thank you very much for your lecture. It is very interesting to know about convex optimization with noise functions. So I would like to have a questions and answer session, and we have 10 minutes for questions. And to make remote colleagues possible to listen questions from this room, please use this microphone to ask a question. So, dear colleagues, any questions? And so I would like to ask one question concerning Lipschitz functions. Did you try to use broken lines approach or this-
Sorry, какой подход?
broken line or
Ah.
Piyavsky methods to use to solve your problem?
Thank you for the question. We consider convex problems. This assumption significantly simplify, how to say, inference, and we do not require a broken line approach. But if we consider non-convex setup, in general setup, maybe it is worth to use. I don't know. I do not think about it. Thank you.
Thank you very much. Another questions? Colleagues?
Может, я тогда по-русски резюмирую, потому что, может, в английский... Ну, время чуть осталось.
Окей.
Значит, прошу прощения за русский, но мне кажется, это важно проговорить еще по-русски, буквально 2-3 минуты. Значит, еще раз, вот у нас есть задача выпуклой оптимизации, и, ну, в общем, методы градиентного типа, они хорошо разработаны. И известно, что, в общем, ну, просто надо идти по антиградиенту, ну и правильный метод, вот он решает задачу, ну, если мы говорим о выпуклой оптимизации. Естественно, для задач, в которых нет градиента, ну и они гладкие, можно аппроксимировать градиент по компонентно конечными разностями. И это тоже неплохо работает, но мы-то работаем с негладкой задачей. И когда вы заменяете в конечной разностью функции модуль x производную по направлению, то производная по направлению терпит разрыв, а конечная разность, она это как бы неправильно улавливает. То есть вы не можете аппроксимировать конечной разностью, ну так, по науке. И возникает много сложностей. Естественно, эти сложности были преодолены, и в принципе оптимальные безградиентные методы были предложены. И до недавнего времени считалось, что эти методы, ну, они оптимальны по числу оракульных вызовов, то есть как бы наука такая более-менее сделанная. Но вот я приводил пример функции вот здесь, которая, ну, понятно, что от того, что нам как бы нет, так сказать, доступа к значению функции точного, у нас возникают проблемы. То есть мы должны не просто ее минимизировать, мы должны учитывать, что она нам доступна шумом. И если задуматься, на самом деле безградиентная оптимизация — это всегда, как правило, в условиях шума, потому что иначе бы была программа, которая бы позволяла делать backpropagation. А раз программы нет, значит, это черный ящик. Значит, это какой-нибудь код, который использует метод Монте-Карло, и чтобы посчитать значение функции, вам надо, соответственно, запустить программу, и чем точнее вы хотите посчитать функцию, тем дороже. Поэтому на самом деле, когда вы работаете с безградиентной оптимизацией, то, естественно, вводить два показателя, значит, сколько вы раз вызываете значение функции, программу, которая вычисляет значение функции, ну и насколько точно она вам выдает значение функции, потому что, если вы, например, используете какую-нибудь симуляцию, то чем вы точнее хотите получить значение функции, тем это дороже. И нам надо одновременно учитывать, насколько большой уровень шума допустим и, соответственно, сколько этих вызовов надо сделать. И вот удивительно, что два зайца убиваются одновременно. То есть вы берете алгоритм, который, ну, очень простой, просто стохастический градиентный спуск с правильной корректировкой того, что такое сток-градиент. Тут как бы рандомизация вводится, вот эти случайные векторы на сфере в разных нормах. И получается, что вы одновременно оптимальны и по числу оракульных вызовов, и одновременно максимальный уровень шума. Вот это совершенно неожиданно. Если резюмировать доклад, то, вообще говоря, ну, это вот правда, как бы не соответствует интуиции, которая есть в оптимизации. Она обычно об обратном, что если быстрее, то чувствительней. Чем быстрее хотите сходиться, тем больше платите за точность вычислений. Вот просто если задуматься, ну, я до этого года был уверен, что по-другому быть не может. Ну, вот просто выкладки показали, что вот бывает так. Вот, довольно интересное наблюдение. Ну и повторю, что задача-то не гладкая, и поэтому то, что здесь работают по-прежнему вот эти вот конечные разности, но это, правда, до нас было открыто, это вот довольно интересное наблюдение. Ну и совсем как бы последнее. Вот история довольно тоже интересная, ведь вот это было известно, да, вот оценка выше, которая. Мы подумали, а почему бы не сделать на один шаре, ну, то есть, и все сделали правильно, но в статье, она в автоматике телемеханики опубликована в 2016 году, там просто опечатка. И из-за этого оценка получилась, ну, хуже, чем она на самом деле была. Французские коллеги, не зная о нашей статье, переоткрыли эту оценку, и они эту опечатку не сделали. И у них получилась оценка просто доказуемо лучше, чем та. Вот. И 5 лет как бы это существовало, или 6. И, в общем-то, оказалось, что такая естественная интуиция, что надо выбирать случайно направление на евклидовом шаре, ну, то есть все направления равновероятны, она оказалась, ну, как бы в целом правильной, но если мы будем брать на L1 шаре, то оценки получатся еще чуть-чуть лучше. То, что тоже совершенно, так сказать, ну, вот передний край науки, и, вообще говоря, только сейчас начали вот это изучать. Ну, то есть, точнее, предложили давно, ну, относительно, но то, что это вот начинает работать, вот статья буквально несколько месяцев назад появилась. Тоже вот хотелось на это обратить внимание. В принципе, я закончил. Если бы я по-русски говорил, я по-русски раза в 3 быстрее говорю, вы, наверное, заметили. Я бы успел побольше, я бы с выкладками что-то рассказал, а так пришлось по-английски немножко. Ну ладно, да, ничего страшного.
Alexander, thank you for your detailing detailing speech in Russian. And so, questions?
Я по-русски понимаю, если что. Времени просто мало остается.
Is there any algorithms which also have high level accuracy as well as kind of very fast kind of.
Я понял, я не знаю таких. То есть,
So
this
is
is the
it the
only one.
first?
Yeah. This is why I decided to talk in, how to say, student event, some advanced result that is, how to say, borderline of modern science. Because, in my opinion, this is something unexpected that contains some deep ideas or can be developed. It's interesting. I was wonder when I first time understand that this is true. It's unexpected for me.
Thank you very much.
Thank
And I would like to ask, are questions from Zoom connection?
Okay.
No questions. Another question from this room? Okay.
На всякий случай я напишу свой контакт. Вот. Если будут вопросы, я с удовольствием отвечу. Мы на физтехе занимаемся, в общем, оптимизацией. Сейчас я к тому читаю курс «Математика больших данных». Там очень много математики и больших данных. И он записывается на видео и транслируется онлайн. Кому будет интерес, все свободно. То есть вы можете просто мне написать. Я вас подключу к этому, там буду расшаривать всякие материалы. Абсолютно все свободно. И чем больше городов в России мне удастся в это вовлечь, тем я буду рад. Все, естественно, бесплатно. Ну и, в общем, просто хочется делиться знаниями.
And so,
Спасибо.
if you have questions after this presentation, you may write from presented email gasnikov at yandex.ru. And so please do not hesitate ask any questions concerning his topic of this presentation. And so, Alexander, thank you very much. And I would like to introduce next presenter from High School of Economy, Alexander Masyutin. Oh, sorry, Alexei Masyutin. The topic of presentation, model, risk, and meta learning. And so we have a small pause. And so, Alexei, are you ready?
Yeah, thank you very much.
Okay.
Good morning or good day. I'm really happy to have a talk here today. My name is Alexei Masyutin, as it was said. Actually, I think my talk would be a little bit in contrast with the previous one, because it is more of a business talk. We will discuss some aspects of applying models in business processes and calculating financial results that those models are being a reason for. And the interesting thing I would like to share with you is the notion of model risk. So basically, when we are developing any model, any mathematical model, which aims to predict something. Every time we estimate the errors that those models are making, and obviously all models have some errors, and it's important to understand which financial impact this or that error can lead to, and therefore we can estimate those expectable or unexpected model risk consequences. So much of this talk would be based on my previous experience at Sberbank, and actually I was working at model validation department, which checks models for their performance to guarantee that those models are performing well in the business process, etc. So, much of this talk was presented before on Risk Minds conference. So it's just to make some reference to the previous previous things. Okay, just a second. Okay, the plan would be as follows. So we will talk about multi-class models. Why multi-class models? Because they're quite popular and there are really many processes that can be described by those models. We will talk about some examples, how those models are working in the production environment. We will talk about their errors, how to estimate them, and how to translate those errors in financial results. After that, we will go to notion of model risk, and we will discuss some approaches how to quantify that risk. So let us just dive in some examples how those models are applied. So there are really many business processes, and I would like to bring 3 examples. So the first one is some IT support queries categorization. So suppose that there is a flow of some messages that are aimed to kind of emphasize that this or that system is out of service and there is some problems in IT infrastructure. And typically the business department will have some IT support department which is receiving those queries and then deciding whether or not we should call that specialist or this specialist. And typically they would be presented in a form of plain text, which is not really structured, and hopefully there are some, categories, but the users can change their own category, or they can describe the problem in their own style. So it's often difficult to automatically predict which specialist, which IT support specialist should tackle this or that problem. So if we talk about mathematical model, the typical model would be an NLP model, natural language processing model, with many classes, and each class will be corresponding to each particular category. For instance, we have systems A, B, C, so the task of the model would be to predict which class this message is relevant to. And some typical instruments to solve those problems, like text preprocessing, which is TF-IDF, using some embeddings, using language models, and to run over that some classification algorithms, which can be actually very simple or difficult. And query types are usually split into classes, something like complaints or gratitude or query for consultation. Also, we can predict which system this message is addressed to. Another example of multi-class models in business processes, and especially in financial industry or telecom or retail, is product offers. Here we deal with several classes which are binded to products. Suppose you have K products, and you have to decide which one is relevant for this particular customer, for your client. In this case, you also have a multi-class models, which are typically built based on client data, transactional data, their profile, the history of their previous purchases, etc. And there are lots of really algorithms to solve these problems, but again, the situation is quite similar. We have some classes, and we have to predict which class is relevant. Okay, in use monitoring, almost the same like the first one, but here we have a little bit more difficult problem to solve, because we have to define this or that news is relevant to this or that corporation, and then to assess some sentiment of that particular news message, which involves some name entity recognition and then classification. Well, those were the examples where the multi-class models are applied. Now let's understand how one can assess the financial impact of those models. To start with that, of course, I think many of you have previously built some statistical models or machine learning models, and of course there are some typical accuracy metrics or model quality metrics. If we start from the binary case, not multi-classification, by binary classification, everyone knows these metrics, these confusion metrics. There are type 1 and type 2 errors, false positive and false negative. Well, it's quite typical, and what this matrix says is that, okay, you have on the one side you have model predictions, on the other side you have the real factual values of your target variable. If we take the product offer case, the target variable is whether there is a response from the client or whether there is no response from the client. And the model predicts either of that categories. So there are some definitions. I think you're quite familiar with that if you were dealing with some machine learning models like positive and negative, which are the numbers of clients which accept the offer and reject the offer. Well, if we go to so basically the previous matrix told us how often our model is true and how often it makes errors. And in this matrix, we gather some financial impact of erroneous decision or correct decision. So I'd like just to discuss those cells in a nutshell. So if our model decides to offer a product and the client indeed agrees to buy this product, to purchase this product, then as a company, the business process generates product margin, which is some profit per 1 unit of product. And we have to subtract the costs of our communication. The true story is that you cannot just offer every client whatever you want, not just because the client might be not happy with that, but also because every communication has some costs, actually, because it can be either SMS or direct phone call, which is billed. And in case of SMS, you pay to the telecom operator, and in case of communication center, you pay for your workforce that is doing those communications. And of course, product margin minus costs is positive value. And if we offer some product and there is no response, we just lose that amount of costs. So in case when we do not offer anything, we do not bear any costs, but we also won't get any margin because our client would not receive this offer. So if you pay attention, it's obvious that a financial result, which is a number of true positive multiplied by those, so to say, net profit margin, minus false positive multiplied by costs, is our financial result, and true positive is negative to false positive, and therefore false positive and false negative errors of our models define our financial results. So we have to minimize them. The true story is that we cannot minimize them simultaneously. We have a trade-off. Okay. What happens when we go from 2 classes to k classes? So our matrix is going to be larger, and we will have more combinations. So, for instance, when our model predicts that this particular client is interested in the product I, and really he or she was interested in the product J, that leads to, again, to some errors that our model bears. And to calculate accuracy ratio, you have to kind of make the sum of this main diagonal of this matrix. Well, to this point, I think it's quite straightforward. If we talk about statistical quality metrics, and of course we calculate them all the time when we build the model, when we train it, when we validate that. But now we have to kind of add some financial kind of consequences of that. And to make it more general, we denote it like by Vij, which is value of the gain or potential loss in case of our model error. So the final financial effect for this multi-class model is this double sum of products of those frequencies, so how often this model gets this error, and we multiply this by the value of gain or loss. Well, these matrices, they are calculated based on historical data. So you have the, so to say, big table where the rows are the clients or the offers to those clients, and somewhere in the columns you have this target variable, which product the client has responded to, or whether maybe the client didn't respond to any product, and you have the number of columns which show the model predictions, so probability for each class. Well, and again, just to finalize this section about model quality metrics, you can use different metrics such as a render curve, and here we have some comparison between binary classification case and multi-class classification case, which are pretty much the same in terms of logics, but they are just redefined in order to account for many classes. Okay, now let's just have some example using some simple numbers. Again, this talk is more like business talk. It's not about strict formulas, etc. Suppose we have this IT or queries categorization problem, and there are somewhat like 7,500 queries per day, and we have, so to say, 3 types like ABC. It turns out that in order to manually categorize one of those queries, we have to spend 10 minutes. And if we estimate that, if we assume that, assume that there is an 8-hour day, we will need approximately 150 employees per month in order to serve this amount of queries. And if we kind of come up with some monthly wage for such a specialist, whatever number, it's just hypothetical, we will understand that to upkeep that manpower, we have to spend something like 400,000 euro per month. And in case if we implement some multi-class model, we validate it on historical data, and we can calculate the frequencies of errors or frequency of correct predictions by the model, and we get this matrix. So here we have, suppose, just again, hypothetical numbers just to give an example. So we have for category A, 120 correct predictions and 10 incorrect predictions. And you can see this in this, you can see this in the matrix. So the category B is the most frequent one, and the model well deals well with that. We can say approximately the same about the category C, but except for the fact that our model sometimes mispredicts this by proposing the class B. So, and ABC can be just different system types. So A is core banking system, for instance, B is the secondary systems, and C some irrelevant, so usual office user software. Okay, we can calculate accuracy just summing up the main diagonal, dividing it by the total number of incoming queries, and we get that 92% of our queries are categorized correctly by the model. Also, we have to understand which are the negative or positive effects of our predictions, and for our case it's quite simple. If the model predicts the class correctly, we do not spend any so to say money on recategorizing that, and we don't have to do any manual work there. And in case when, suppose, we predicted the class wrong way, it means that we have to actually ask the human to recategorize that using manual force. Again, if you multiply and sum those frequencies and the values of errors, we will come up with the sum that is derived here. It's like 31,000 euros, and compare it with the initial 400,000, which shows a really great improvement in terms of financial result when you apply such a model. So there is no surprise. Okay, we have a rather accurate model, more than 90% of accuracy. We're implementing this model in the business processes, and we kind of enjoy the financial result that this model produces. And instead of upkeeping 150 employees, we can just solve this problem using 12 employees and upkeeping and maintaining the model in the production. So this is basically how we can calculate very easily the financial effect for multi-class models. And here we have a kind of question. Suppose we performed these calculations based on historical data, based on out-of-sample data. We validated the model, but when we keep using the model in our production systems, the interdependencies are changing, and typically the quality of the model is going to decrease because the model is not updated. You have to, from time to time, to retrain this model. And actually, to retrain the model, you need a bunch of data scientists, data engineers, etc. So it's also not so cheap to do, and therefore you want this model to live some time. And when it happens, you have to account for model risk. So what is model risk? Okay, we can go also with the non-symmetrical matrix gain case. Well, basically it accounts for that not every error are equal in terms of financial results, so they can be different because when the model mispredicts the core banking systems case, the loss is greater than when we compare it to just MS Office software. It's just another example that those gains or losses can be non-symmetrical. However, the logic stays the same. We multiply the frequency of the error with the loss corresponding to that cell, and we sum this matrix. Okay. So here we coming to the model risk. What is model risk? When we perform validation of the model on historical data, we can use just point estimate of accuracy, which is just calculate some quality metrics on the data set. But actually, we can do some bootstrap techniques, or we can do some cross-validation and get a row of metrics, and then they form some distribution. So this is a more natural way to deal with it, because in real production, we expect the model to decrease in terms of its performance. And when we have just one value, it doesn't describe the process well. Therefore, actually, we build some distribution on our accuracy, and we come up with some, so to say, confidence interval. And it's common practice to kind of be a little bit conservative about your model performance in the production, and to not to use the point estimate, but rather to use some left-hand side confidence interval. And as soon as if we bootstrap our data, we every time can recalculate the confusion matrix, calculate the financial effect, and come up with, so to say, dual distribution, which describes the financial results which our business process will generate, subject to that particular accuracy that is observed within the data. And it happens that when we deploy the model and when we use that in business process, we expect that our financial result would be like point-wise estimate on validation sample plus minus this confidence interval. The interesting thing to plan about your business process is how wide this interval can be. I mean, when we come up with a model on the development stage, we expect some quality metrics, and we plan the business process and expected profit, understanding that this particular model will generate that result. In practice, we know that the result is going to be lower, and we have to account for that in our planning. Therefore, the task of model performance prediction is really important. Here we can transform all those statistical quality metrics to business process metrics. So finally, suppose that we have lots of model in the processes. As we discussed, it can be query categorization, product offers, etc. Each of that models generates some a lifetime performance metrics, which can be calculated on different months or weeks. It depends on the frequency of our data infrastructure and well, basically there is a term about target variable horizon when it can be observed. And it turns out that each model can produce some distribution of equality metrics, and then we can combine them to final financial result distribution. In these terms, when we have a large portfolio of models within our organization, we can think about the model risk as that financial result distribution that is driven by uncertainty in model quality metrics.
Да, я могу начинать. Dear colleagues, let's start our student session. We start with the talk of Andrei Filchenkov. Andrei, can you hear us? Okay. We can see you. But we do not hear you.
You do not hear me.
We can hear you. But
That's perfect. So yeah, I would like to share my presentation. Do you see it?
yes, we can see your slide. Андрей, я уже боюсь что-то сказать. Сейчас получилось. Так.
Start.
Андрей, you can start.
Yeah, I have echo. Sorry, let me. So yeah, I'm turning off microphone so you can tell me that I can start, and then I would go. Oh, perfect. So thank you, everyone. Hello, and great to see you on the conference. My talk is multi-agent reinforcement learning for multi-vehicle, one commodity vehicle routing problem, which was done with my student, Yamin Habib. So there are plenty of routing problem family formulations. Maybe the most known is trolling salesman problem, which is how to go with one, let's say, vehicle across the whole graph. But there are a lot of other different formulations and different problem settings, which can be different from the very simple and with less constraints to the most complicated with the most constraints. This is caused by the high variety of real-world problem settings. Okay, so this is explained by the high variety of the real-world problem settings. Here we have maybe the most generalized problem setting, which is called dynamic and stochastic capacitated vehicle routing problem, which is DSCVPR. So here we have a lot of vehicles which should. You can imagine taxi. So you have many cars which should take people from one point to another point, and these orders came up not at the beginning, but due to the performance of the system. So here we have maybe the most generalized problem setting. And there are lots of approaches which can help to solve it. The main problem here is that most of them are non-adaptable. So once you change the graph, once you change some constraints, these approaches would not work. So you have to run them from the scratch. And what we here is aiming to is to apply multi-agent reinforcement learning approach that can help us to access adaptivity of the approach of the solution. And here we try to apply this approach to solve DSVPR. The contribution of this research is the following. So we propose a new method to handle this problem in the multi-agent reinforcement learning setting. We also propose a new method for training such reinforcement learning based agents. And we also created a simulation system to develop and test methods for working with the DSVRP problem. So first, let's come to the setting. We have multiple vehicles. We have dynamic requests on how much weight should be placed. Each vehicle has some capacity, so we cannot use just one vehicle to take all the orders and then put them. And each request, so we cannot just take more than we have. There is an update rules. So once a vehicle comes to a point, if it has enough free capacity, it can take the order. So we just move from, so request is 0. And if the vehicle comes to a point where this request should be put, it also can put it. So the request is 0. In the generalized setting, it's better to think not about just taxes, but more about, let's say we have a lot of factories, we have some spots that can consume. So in factories, we have a positive amount of the goods. In points of consumption, we have negative amounts of goods because they want to consume something. And our goal is to somehow put the vehicles in a way that they can most efficiently provide consumers with the goods produced in the factories. So this is like extremely popular setting because in logistics, you met this every time. For instance, once you have a lot of restaurants and a lot of clients for, let's say, Yandex Food or Delivery Club, they solving actually the very same problem because they have only a limited amount of couriers, and the couriers have only a limited capacity. So they cannot go to all the restaurants, take all the orders and go to the clients. No, they should actually serve the clients one by one with a very actually big, but not unlimited amount of space behind their back. So what we actually try to maximize, we need to maximize, or in our case, minimize the cost function. So moving is not free. Actually, we spend, let's say, oil or time, and each age is associated with some cost. And what we want to do, we just want to minimize the cost of all transactions. So all the vehicles is going somewhere, and we want to minimize these transactions. Given that in the end of our session, all the requests are satisfied, which is service quality. So all the requests are equal to 0 at the endpoint. There are lots of methods to solve this because the problem itself has a long history. So there are exact methods. Most well-known are branch and bound, branch and cut, but also constraint programming comes to the game, and we use a constraint programming method as a baseline. So the problem is that it's really scalable, and any change involves rebuilding the solution from the scratch. So more popular are heuristic methods. So there are lots of them. The main problem here is they rely on handcrafted heuristics, so they have biases. They cannot anyhow learn from the experience, and we cannot actually guide them to find better solutions because they use the heuristics on their own. Another branch is deep learning methods. So it started with recurrent neural networks, then pointer networks came, and these days the best solutions are based on multi-head attention and transformer. So we use one of them, the best one, as the baseline for our solution. So first we build a simulation system. So here we have a graph. Yeah, I wouldn't go much about this. In general, we just have vertices of the graph where we should make a decision where we should go. And we also build a simulation of how this request can come up to the game and where these vehicles could be located in the beginning, what is the capacity of this vehicle, so we can simulate different conditions. What we actually propose here, so first of all, let's go how we represent the graph itself. So instead of using coordinates, for instance, or something, we used non-trainable graph embedding, geometrical Parsing eigenmap embedding, GLE. It has lots of nice properties. So actually, briefly, it helps to use embeddings as the input for agents, which represents the, let's say, geometry of the graph and helps agents to understand where they are. So as we use reinforcement learning, we need to give an agent environment representation. So in our case, we use 3 blocks. First is current node, where a vehicle is. So it's just the embedding, as I told. Also, we have a matrix of requests. For each vertex, we know what is the request. And also, we have a matrix of vehicles. For each vertex, we know where a vehicle is and its current capacity. So 3 of these blocks are used as description of the environment. As for agents, so we used multi-agent reinforcement learning, and we decided to place agents in nodes of the graph, not in the vehicles. There are 2 reasons why we decided to do so. First of all, it's really scalable in terms of how many vehicles we can use. In general, it's hard, usually, it's hard to rebuild the graph. It's not such necessary because graphs changing not so dynamically. What actually changes dynamically is the number of vehicles. So if you come back to the delivery club, you can hire new people, or you can just, if it's not 10 minutes, okay, 8 minutes. So you can come up to a solution where you have to reduce all the vehicles. So this is why number of vehicles is not the constant. The constant is the number of nodes in the graph. So also we tried 2 algorithms. One is based on DQN. So here, okay, I think I should skip details. Actually, we just, anytime we should make a decision where a vehicle, if the vehicle is in this node, where it should go, knowing all the information, and the reward is the how much we earned in terms of the cost function introduced previously. Also, we used PPO, proximal policy optimization. Actually, it has similar logic in terms of how we implement it in the graph, but we used another reinforcement learning algorithm, so the architecture of the network was different. It's actor-critic based architecture. And we also created 2-phase learning. The first phase was pre-training of the agents with no capacity and weight constraints, because we find out that this pre-training is extremely helpful, because without this pre-training, everything crashed. And the second phase was considering all the constraints. So we just had a fixed amount of episodes after pre-training. It's like 500. So this is how GLE plus DQN worked. So the first phase was trying to reduce the error, and then the second phase, when we added constraints, it also reduced the error. So for PPO, we tried different architectures and different hyperparameters and settings, but nothing helped. So the first phase even didn't came up to a solution. So as the baselines, we used Google OR tools, that's a CP subsolver, and Mardan, that's a transformer-based architecture. So here you can see how much time, the cost function was time. So here you can see how much time was spent. Actually, the solutions quite similar.
Андрей, вы не имеете уже время, доклад было меньше 10 минут. 8 минут у вас было, вы уже 12 минут говорите. Так что, если можно, надо как-то закончить.
Two main things with this comparison. First, Google OR tools are totally non. So we just discuss comparison.
Андрей, вы слышите?
How well we can work with subsolvers. For Markdown, itself, it has almost 700,000.
Он, по-моему, нас не слышит. И мне кажется, он просто продолжает доклад делать.
Depends on the number of nodes. It has, but when you have the most number of categories. We have 2 times more. All other cases have a smaller number of categories. So our solution works. And the same plus we can see that this works well. It works. You can come back. So thank you very much.
К сожалению, у нас нет времени на вопросы. Мы довольно сильно сейчас уже не укладываемся в регламент. Давайте поблагодарим докладчика. Андрей, спасибо. И у меня очень большая просьба ко всем последующим докладчикам. Пожалуйста, смотрите на расписание. Сколько у вас времени на доклад? По-моему, тут у всех 8 минут на доклад. Очень прошу следовать регламенту. Потому что просто иначе ребята не успеют покушать. Вот в столовой тут все довольно жестко. Мне так объяснили. Вот. Спасибо, Андрей, еще раз за доклад. Прошу прощения, что вынужден был вас прерывать. Итак, следующий доклад Маргарита Мишина. Next talk Маргарита Мишина. Вот, тоже онлайн. Маргарита, вы здесь? Маргарита, are you here? Okay, let's start. You have 8 minutes.
Okay, can you see my screen? Okay, good afternoon. My name is Margarita Mishina, and today I will speak about modeling mobility graphs for evaluation of urban accessibility. First of all, it should be noted that we consider the urban accessibility in terms of coverage of places that a person is able to visit under existing space-time conditions. Therefore, this concept is strongly related to peculiarities of pedestrian infrastructure and transport system of certain city. Actually, the task of assessing transport and pedestrian accessibility of urban areas is one of the most important computational tasks of urbanism. This is because many applied tasks of urban environment analysis are based on determining proximity and accessibility of urban facilities and services for citizens. Depending on the type of traveling to the destination, 3 general types of accessibility are evaluated. These are pedestrian accessibility, accessibility by public transport, and accessibility by private transport. Pedestrian accessibility assessment are widely used to solve the problem of providing the population with services that are needed in the immediate neighborhood of residence places. For example, this is relevant for kindergartens, schools, pharmacies, playgrounds, and others. In this case, we have to consider existing pedestrian barriers, for example, blocked sidewalks or road without crosswalks. And that's actually why we cannot use just a radius for assessing accessibility, as it's suggested in most regulations. The accessibility by public or private transport is used to evaluate provision with services that mostly cannot be reached by walking. But there are a lot of difficulties when we're trying to build complex model of transport system related to collecting information about traffic jams, features of the traffic organization, and public transport operation. But the point is that the creation of such detailed model is it's very costly, first of all, and not always justified. Therefore, to deal with the problems that are peculiar to common approaches, we present a new method for assessing urban accessibility based on an intermodal mobility graph. And basically, the intermodal mobility graph represents all possible ways to travel from one point of the city to another, including pedestrian paths, traffic roads, and public transport roads. All necessary information about these infrastructures can be uploaded from OpenStreetMap and processed by high-level Python packages. The main steps to be taken to build the graph are presented on the slide, and the first step, of course, is preparing the data. From OpenStreetMap, it's possible to get coordinates and some semantic information about pedestrian roads, driveways, and public transport roads. After that, since we have sequences of coordinates that describe linear objects, we have to reconstruct pedestrian network, driveway network, and public transport network separately. But here we're faced with the first problem. Open geographic data often contains many topological errors, which are considerable for us in this case, and which must be fixed before building the networks from these objects. The slide shows the most common topological errors that must be corrected to get connected lines of networks. The next step of the processing data is essential to connect 3 different networks into the intermodal graph. So how do we do this? The main idea comes from real life, and to put it simple, when people move around the city, they probably start from random point on the street. Then, if they need to use public transport, they walk to the nearest appropriate stop, get on a bus, tram, or subway car, travel to another stop. Maybe they change a mode. For instance, after subway, they might decide to get on a bus. And after that, they finally walk to the destination point. So, to make it possible to consider such complicated roads, we have to add passages between the pedestrian network and 2 other networks as shown on the slide. But at this stage, we still have 3 separate networks that actually might be represented as the graphs with nodes, edges, and associated attributes. And basically, after union of these 3 graphs, we finally get the intermodal mobility graph. Since now we have the intermodal mobility graph, we can proceed with the accessibility assessment. And as I said at the beginning of my speech, under urban accessibility means coverage of places that a person is able to visit under space-time conditions. And most accurate representation of the accessibility is an intermodal subgraph, in which total age, weight, travel time or distance, from the start node to all other nodes do not exceed a certain value. This is actually a well-known single-source shortest path problem, which in this case is sufficiently solved with Dijkstra algorithm. And the example of the subgraph for 30 minutes travel on foot and by public transport from some point in St. Petersburg is shown on the slide. And also here you can see a polygon, which is called an isochron. The isochron is simpler and more visual representation of the accessibility, which derived from subgraph, using formula shown on the right part of the slide. Thus, both accessibility subgraph and isochron cover the territory of the city, within the boundaries of which it's possible to move from a given point in a set maximum time along the shortest intermodal roads, including moving by public transport and, of course, by foot. The main advantages of this method is that it can be used in clarifying the regulatory accessibility and provision of urban services to the population, and actually many other applications in urbanism. The versatility of the presented method based on open data allows us to quickly assess accessibility of services for any city, as well as make reasonable forecasts with changes to the transport model, for instance, when new public transport routes appear. And this concludes my presentation. I want to add that we provide all necessary code for building the mobility graph, accessibility subgraph, and isochron in our labs library that is called CityGetTools, and that will be able as soon as it's approved by the university. Thank you for your attention. I'll be glad to answer any of your questions. And that's all. Any questions?
Спасибо. У вас очень хороший английский. Да, но по аудитории пока вопросов нет. Спасибо. Меня слышно? Ага, все. Отлично. Тогда переходим к следующему докладу. Давайте поблагодарим докладчика. Спасибо. Следующий доклад у нас очно будет. Значит, Алена Козырева, Алена присутствует? Да? Она будет понятно. Да, ну прошу прощения, да, доклад Алены Козыревой будет онлайн. Алена, вы здесь? Да, я вас вижу. Все, пожалуйста, начинайте. 8 минут. Просьба не забывать, что доклад 8 минут.
Can you see my presentation? Okay, so my name is Elena Kozareva, and I'm going to present our research on the topic of development of method of assessing the safety of the urban environment based on the analysis of the communication practices of city residents in information services. One of the main tasks of managing city structures all over the world is to ensure the safety of the citizens. And the concept of a safe urban environment includes not only the degree of protection of the population from criminal threats, but also factors such as the environmental safety of the city, a safe and comfortable place to work and relax, the exclusion of risks of accidental injury to the population. So in this research, we analyzed the communication practices of city residents who leave reviews in information services about parks and squares in order to identify markers of safety and comfort. So we analyzed parks and squares in 19 districts of St. Petersburg and selected 318 objects of improvement, and the reviews were uploaded for each object. As a data source, we used Google Maps, one of the biggest services. Google Maps make it possible to leave comments about the location. Anyone who has visited an object of the map can leave a review, and in addition to numerical evaluation, there is also an opportunity to leave a text comment. Now, it was planned to receive reviews from the Google Maps by downloading via the API. However, the Google API makes it possible to upload only 5 reviews, and we chose Outscraper service. As the first stage, we collected reviews from the park cards, and later we left only those reviews that are related to security. So we received feedback on 18 districts of the city. Then the received array was processed, and we created a program script that searches the keyword which relate to security. And the dictionary was compiled based on the results of a social survey. The main security markers were identified, and after that, we evaluated the tone of the comments left and assess safety of urban object as positive, negative, or neutral. Here you can see the general scheme of work with the stages of data processing. Here you can see an example of how the service may look like. So the received data with estimates can be geocoded in JSON format and transmitted to the map to build a heat map of the safety of urban facilities. The database of reviews can also later be expanded with other sources. For example, posts from Twitter can be used as a second source. As for data processing, we collected more than 470,000 reviews of parks and squares in 19 districts of St. Petersburg. And from this amount, we selected 27,000 reviews, which describe various aspects of safety and comfort of the park. Most of all, residents of the city write about road and transport safety. There are also many reviews about the organization of the order, and this category of reviews creates a feeling of comfort and security. The table on the slides shows examples of reviews on the topic of security in one of the most popular parks in St. Petersburg, 3000 University Park. The rating is 4.7, and total of almost 42,000 reviews have been left for it. And in the table, you can see the percentage of topics on which the reviews have been left. There is also some examples of reviews received from Google Maps. And after processing, it contains only text of review and a link to the review on the Google Maps. There is also some risk of fake reviews or reviews left by bots. So when studying our user data, attention was drawn to such factors as a strange nickname, small or excessively large number of reviews, or an empty profile. So during the review of the selected account, it was revealed that only 7 of them were bots. And we also contrast automatic moderation, which is carried by Google Maps, because it's more likely to publish reviews from person who visited the location in reality with turned on GPS, so offering to leave a review after visiting a place. And the categories of safety of green spaces were determined on the basis of a social survey. And after analyzing the user reviews, we identified various problematic aspects of the city's green zones that correspond to the survey results. Automated feedback analysis has proven its effectiveness, and that is why it can be used for mass monitoring of urban infrastructure. So we conducted a study of the safety of park areas in different areas of large metropolis based on the analysis of the communication field of geoinformation services. And we can say that this type of analysis is more economical and faster than the classic questionnaire, and can be used by the city administration for operational analysis of information. That's all. Thank you for your attention. Ready to answer your questions.
Спасибо. Так, есть ли вопросы? Да, пожалуйста. Сейчас. Есть другой микрофон, как можно? А?
Do you pay attention that some users make only 1 or 5-star rate on Google Maps? Is it fake review or not? Do you pay attention that some users get only 1 or 5-star rating on Google Maps? Is it fake review or it's normal? How you analyze it?
You mean rating of users themselves? Or the reviews they leave?
Can you repeat, please? I don't hear.
You mean the rating of a person on Google Maps, or the rating of a review they leave?
I'm about that some users can make only 5 or 1-star rating on places in Google Maps.
Where there is not only the rating but also the text. So we look at text and the numerical value in general.
Thank you.
Thank you. Let's move to the next talk. Thank you. Thank you. Let's move to the next talk. Let's thank the speaker again. And move to the next talk. Next talk is the talk of Alexander Antonov, and this talk will be offline. Наверное, так, да?
Презентацию могу переключать сюда. Good afternoon, dear colleagues. I want to present you the results of our research. The goal for this research is to develop new method of e-participation data application in long-term planning and urban management. And okay, so nowadays most of public government relationship in the fields of urban management goes through digital channels. For example, non-emergency city service requests from citizens as part of e-participation data goes through e-participation services, and they in a lot of ways are similar to CRM systems which process complaints and suggestions from customers. The similarity between the city service requests complaints. Okay. So this similarity between city service request complaint services and customer relation systems leads to the same functional goals: high-speed problem solving and positive assessment from citizens or customers. With these goals, most of city requests services have assembly line style request processing. They process requests in assembly line style, one by one, as fast as possible, with attention to current results. And this style results in missed opportunity of larger scale analysis. From this perspective, single problems can be perceived as a sort of a symptoms of larger complex problems in urban environment. Our approach can help with the detection of hidden processes and save resources from expenditure on recurring problems. In this work, we present an algorithm which based on such approach. Next, I will describe current framework of request processing, digital event model, the main part, situation detection algorithm, and the test of this algorithm and its results. We based our research on our St. Petersburg portal, development of digital public to government relationships lead to significant increase in volume of feedback, and as a result to streamline process of request processing. An example of such framework is the workflow of our St. Petersburg portal. Here all process of processing from citizen of signal processing from citizen to executor and back with the answer takes from 3 to 30 days. And with the exception of repeating problems with same location and problem type, this workflow doesn't take into account links between requests. However, these links can provide helpful insights into more complex events happening in the city. In the proposed algorithm, situation is a time-limited systematic anomalous event which contains a set of incidents with common cause. Situation has two base characteristics. It is duration,
number of days with at least one active incident, and intensity, current or mean number of accidents or incidents per day. As for incident, it is, for example, one complaint or one message in a social network, and it should have location, physical coordinates, time, and problem type. With these three characteristics, we add three classes: physical, functional, and management. And for example, some incident can happen in city block with damage to pedestrian walk, and it will be managed by local administration. How much time do I have? Okay. And now to the algorithm. The first step is data enrichment. We add classes and place it in digital model of city. Then we set timeframes for the problem, and these timeframes we get from a classifier of service. And in modeling block, the process of request processing is simulated with the time flow. Each day new incidents are added, current terms are shortened by one, and incidents with expired terms are removed. If the situation have 0 accidents, it is considered closed. So we tested this algorithm on dataset with residential buildings class of physical objects during January to July 2022. We assign each incident to a building via spatial overlap, and then model and detect situations. As you can see, there are some buildings with long periods of high activity, and this can be considered as anomalous. So we can see these buildings here on the diagram. On the horizontal axis is duration, and vertical is mean intensity. And we can classify them, for example, via medians on each axis, and public managers can pay more attention to situations with to objects with long and intense situations. As for the future work, we plan to test this algorithm on other types and sources of e-participation data, adapted for social network data via topic modeling, and we plan to conduct deep analysis of situations characteristics with the use of machine learning algorithms. Thank you for your attention. Any questions?
Спасибо. Есть ли вопросы? Так, ну хорошо. Если нет вопросов, давайте еще раз благодарим докладчика. Спасибо. И переходим к следующему докладу. Он будет онлайн. The next talk is the talk of Yulia Sergeyeva. Юлия, вы нас слышите? Ага. Так, я понял. Надо просто звук надо сделать. Хорошо, Юлия, вы можете начинать. Да, можете начинать.
Location of user post in social network plays an important role in a wide area of research. These researchers are devoted to the analysis of the urban environment based on social media data. It allows us to correlate information about the real urban object with its description in social networks. Information analysis of extensive urban sites is particularly difficult in such study. Publications correlate with market geotags extremely unevenly, and users of social networks often intentionally indicate incorrect geolocations. For example, in order to increase the popularity of their publications, users can also accidentally indicate the wrong or inaccurate location for their publications. Our task is to develop algorithms for recovering the correct information about publications because accurate data on the urban environment improves the quality of a smart city map. An example of a broad area in which social media data analysis can be successfully applied is the study of the urban environment. Location-based social networks are the most useful for the urban researchers. Geotagging provides meaningful information about the objects of users' intention. It allows users to correlate the post with the real elements of the urban infrastructure. This study is devoted to the methods for reconstruction of irregular locations and creating location description for extensive urban sites. This research based on the analysis of Instagram social media post data. The study uses additional information obtained from the collecting and analysis of data from the OpenStreetMap. The complication that we face in the process of research and development is the problem of k-future of many location-based social networks, including Instagram. The list of locations available for tagging is predefined and not expandable. This introduces a strong bias into the data and can negatively affect the quality of urban analysis. We assume that expanding list of locations and extracting additional information about them will help restore the correlated locations of location-based social networks publications using semantic similarity. We describe and consistently use the following methods to bring from the text of publications on Instagram to a form that can be perceived by the model. We clean up the text, limit case, extract hashtags and emojis. The model from ALAP marks up ads and excludes them from the dataset. Overpass query language in Overpass API use the retrieve locations with additional description within a polygon of extended object. Google Translator Python package used for work with different languages and translation to uniform English language. Transformer model Roberta base used to solve the problem of extraction named entities near. Spacey package include model for text vectorization is applied using the built-in word-to-vec model. Finally, Spacey also checked semantic similarity for each post's text and each location from the extended list. The study used historical data obtained from the social network for St. Petersburg for the period from January 2018 to April 2020. Ilagin Island was chosen as an object of study. It best reflects the characteristics of the extensive urban site with an even distribution of post by location. Final dataset contains 172,000 posts, which include text caption, time of publication, map information, and geolocation mark. As a result of the analysis of the data, it was found that there are 27 different locations in the dataset. The distribution of posts on the identified locations is unevenly. Most of the posts refer to main locations, which refer to Ilagin Island in general. This is a problem of data bias and incorrect geotagging. The slide image shows the basic locations of the social network, and on the next slide you can see how the number of geotags has changed after the expansion. The list of geolocation for chosen polygon has expanded with the geodata from OpenStreetMap, its external sources. The OpenStreetMap database has the most detailed information about the object and maintains free access to itself data. The number of information locations has increased from 27 to 66. Most of additional locations contain a detailed description and additional metadata, which is used in vectorization and semantic similarity assessment. Example of additional information are given in the table about 5 objects. The next step after expanding the list of locations is to apply the model for NEO in text of Instagram posts. The text of all posts is translated to English as the trained model, spacey model for English provide more labels for recognized named entities. Transformed model Roberta trained for English is used to solve the problem of extracting named entities. And the model contains following components: transformer, tagger, parser, ner, attribute, ruler, and limitizer. From the total number of labels of named entities, labels are selected to search of mention of locations within the boundaries of an extended object. Presented in the table, as the total number of posts in which named entities were recognized in 22,000 posts. As a result of identifying the entities in the post, a text was formed from them. This text comparable to the list of geolocations, and the selected entities were combined into a single text, which was subsequently compared with the expanded list of locations. After calculating the similarity between the found nears from the Instagram posts and locations from the extended list, all posts were distributed among the 64 out of 66 filtered locations. The distributed of posts by new location is shown in the picture. The number of posts related to locations varies from 3 to 5,000, and the most mentioned locations is user text remain Typico and Ilagin Island. As a result of the study, methods for recognizing correct locations and creating location description for extended object site were created. They're based on the analysis of Instagram social media post data and additional information. This information obtained from the collection and analysis of data on OpenStreetMap. The developed method allow us to take advantage of location social network. Then that's semantic linked using word-to-vec similarity model to the location from the extended list, and that allowing to correlate the post and the new recovered location to which it belongs. The implementation features of the method make it applicable for use with publications and in any language. The plan for further work in the study of other way is enrich geolocation data way to use images and the meta information for more accurately linking of publications with selected geolocations. Thank you for your attention.
Thank you. Thank you. Please, questions? We have time for that. Yes.
Have you got any results in linking images and geolocations? Have you got any results in linking images and geolocation data? Or it's just future work?
Because we haven't kept in database from Instagram, we use only text data for find named entity relation.
Okay, thank you.
Thank you. More questions? Okay, if there is no more questions, let's thank the speaker again. And thank you. And the next talk is offline talk of Georgi Koncevik. Georgi, please start. You have 8 minutes.
Thank you. And today I want to tell you about the results of our work on modeling the citizens' settlement in residential buildings. Включайте, пожалуйста, презентацию. So imagine that you're running a vaccination campaign and you want to focus your efforts. And in order to do that, you need to know where live the most of high-risk groups, or maybe the most of elder people. So you need to know the age structure of the tenants in the blocks. Or another example, let's say you want to develop a playground infrastructure for youth, and for this purpose you also need to know in what blocks, let's say, we live most. And here's the problems that you'll face if you try to answer that questions, which I mentioned before. Let's have a look on the data. So we used the census data, which provides us the age sex distribution on administrative unit and municipalities levels. We also got results of social service from our colleagues on administrative unit scale. Clearly, you can approximate population of houses from this data. So we need to know something about buildings as well. So what we did is that we restored the missing data in the buildings data set, found the maximum amount of citizens that could live in the buildings, and then we found a probable amount of tenants, which obviously was less than maximum one. And then we matched that data with the census data to match it in total numbers. And then we found a share of social groups in each municipalities and in each house as well. So let's have a look on the buildings data set. We got some information about buildings, which is foundation area, number of stories, living area, and sometimes we new number of residents. You can see here in living area series that bold numbers which were restored during the restoration process. Yeah, and as I said, we found maximum number, expected number of residents for each house. There's some buildings on Vasilevsky Island. And then we balance it for the municipality. So how we balanced it? Obviously, the total number of expected tenants in municipality or in an administrative unit didn't match with the census data. So we found the house with a maximum relation of expected population to the maximum population, and kind of kick out someone from that building. And we repeat that step until the numbers matched. So here's an example how it was and how it became after balancing. So I think it's clearly seen that numbers changed significantly, especially for big buildings. Here's how differs expected number of population and balanced number of population with initial numbers on the left and to the maximum numbers on the right. It can be clearly seen that balanced values are closer to initial ones, and expected values, which don't match with census data, closer to maximum values. So here's a picture of how population changed for each building in the city. I hope you can see that blue buildings, which are outliers, in these buildings, population changed dramatically. And civil servants need to check that buildings because data is absolute mess. I mentioned before that we got results of social service of different social groups. So let's say we want to plan parking infrastructure, and now we know the exact number of motorists, for example, in each house, because we found the population, like age, sex, structure for each building, and now we could find share of each social group. And knowing the structure for each house, we could restore the numbers for the whole city, for each municipality, and administrative unit as well. That's it from me. I'm ready to answer questions if you have some.
Thank you.
Thank you.
We have time for questions.
Huh?
Okay.
So no questions. Okay, thank you.
If there is no question, let's thank speaker again and move to the next talk. Next talk will be a talk of Yulia Krasnoperova. Здорово.
Hello everyone. The topic of our research is a method developed for selecting street road network section to create pedestrian public spaces. Research showed that walkability is one of the components of urban livability which contributes to the creation of a sustainable urban environment. Pedestrianization of streets has an ecological and health improving effects on the city, and urban resident contributes to increase in physical and emotional health for a person, promotes not only walking but also the use of public transport and cycling in combination with walking. On the economic side, pedestrianization of streets is expressed in the growth of business profits and tax revenues to the budget and the attractiveness of the city. The social dimension of the impact of pedestrianization streets on the city is expressed in the formation of additional public spaces that create conditions for people to interact with each other, provide a variety of activities. At present, there is no unique integrated method. Decisions to limit traffic are made by experts in transport planning, architecture, or urban planners, and the streets are proposed by citizens or urban communities. To form a full-fledged public spaces on pedestrian streets, it's necessary to determine the most important criteria. The analysis of indicator of which will show the need, the possibility of restricting traffic and potential of street as a public space. The main criteria similarly are proposed to be divided into 4 groups: environmental, social, economic, and mobility. As part of the environment aspect, it's proposed to take into account such environmental indication as the level of noise and the level of pollution by vehicle emission. The social dimension contains such valuation indicators as provision of the district city with the various public spaces and mixed use of building located on the link. The first indication shows the need of increasing the number of public spaces due to the pedestrianization of the street. The second shows the potential for use the popularity of the street during the day. The economic aspect contains an indicator of the number of points of attraction located on the street. As part of mobility creation, is proposed indicator for traffic congestion and the level of pedestrian activity. As a method for selection section on the road network for creation pedestrian public spaces, it's proposed to develop a decision support system to restrict car traffic and identify streets for pedestrianization. Approbation of the developed method will be carried out in the central district of St. Petersburg. The main participants of the system are administration of the city or district and different specialists. In the first step, priority areas and areas of study requiring development are identified. Next, the primary data collection takes place according to the proposed criteria and their analysis. The collection is carried out mainly in 4 ways, using various existing services, using transport model of the city, use different published method and field studies. data analysis in various geographic information systems, or the use of programming languages. So, for example, noise indication were uploaded using the emission model for MATSIM from the transport multi-agent model of the St. Petersburg agglomeration. To determine the mixed use of housing system located on the link, the mixed use of each building located on the link is estimated based on the open data, and the presence of different functions on the street road network segment is identified using a Python code. In order to draw a conclusion about the possibility and expense of restricting the movement of cars on the street, it's necessary to evaluate all the collection indicators to certain criteria. In the form of points on a scale from 0 to 10 for comparison of indication based on existing rules and recommendation. All integral assessment of indications can be conditionally divided into two groups: important, necessary, and possibility of restricting transit traffic, and the potential of the street as a pedestrian one. The scores of the indicator are added up. The number of points scored on the introduction scale will serve as a conclusion about the need and potential for pedestrianization of the street. The choice of scenario for pedestrianization in the near future are proposed to made on the basis of the points scored, as well as an assessment of the level pedestrian activity. As a part of the article, it's proposed to test 3 scenarios of different scale on a transport model, namely several streets in a tourist center, a system of streets in a popular recreation area, and 1 street in a residential area. After the conclusion is made in the direction of restricted transit car traffic on the streets, it's necessary to proceed to checking the traffic restriction on the transport model. In order to prevent the deterioration of existing transport situation and check the average travel time, that it will not change or change slightly. The table provides a brief description of the result obtained. Changes in the average travel time in all 3 scenarios are within 3%, which slightly increases the average time of transport correspondence and can be considered within the margin of error. In the first 2 scenarios, no new traffic jams appear. In the third, the load level increased on some streets. The advantageous characteristic of all 3 scenarios is located on the street near tourist and walking streams. Among the general disadvantages, one can single out the negative perception of the changes by citizens, the high demand for parking in the section of the road network, and the third scenario is characterized by movement of traffic jams and the formation of new ones. The method developed and tested in the Central District of St. Petersburg can become a tool to help city planners, transport specialists, and administration of cities and district make decision of pedestrianization of streets, both on temporary and seasonal or permanent basis. The developed method can be used not only for analysis the most popular and possible streets for pedestrianization, but also make decision about reducing the width of the carriageway or parking space and expanding sidewalk. Thank you for your attention.
Thank you. Thank you. Any questions? Okay, if there is no questions, let's thank the speaker again. Thank you. And we move to the next talk of Alexander Hrulkov. The talk will be online talk. Alexander, I guess you can start.
Я полагаю, что работает. Ладно, я надеюсь, что оно работает. Презентация. Я надеюсь, что что-нибудь видно. Скажите мне, пожалуйста, что что-нибудь видно, и что я могу начинать.
Начинайте.
Можно махнуть в камеру, я в целом вижу.
Все отлично, мы вас видим, слышим.
Рано. Все, да?
Можно начинать.
О, все, супер. Andrew Rudkov, and today I would like to tell you about my study city services provision assessment algorithm. The problem of provision assessment is an important part of urban management, in particular providing the citizens with social benefits and the fulfillment by the government their obligations to the population. This is not a new topic. There are many approaches and methods, but the moment of scientific study of citizens' behavior is the main task. So what is the provisions is? Since citizens' behavior can be nonlinear, such system can be solved, especially for large cities, using math programming methods, and this problem is similar to the transportation problem. But they are solved very poorly or do not solve it at all in the case of nonlinear approaches. The topic of the study was the creation of an algorithm for assessment the provision of the population uses any patterns of demand for a particular type of services. You can see the example of distributions which we tried to apply. And this was the task of provision assessment is for given demands for particular type of service for residential buildings and given capacity of services to satisfy this demand. Taking into account restrictions of the accessibility zone of the maximum distance, which can be set by law, which can be set by specific law of the given type of services. In this case, distribution law is the probability of using the service by citizen depending on the distance. So it's literally the transportation task, but with the specific limitations. And this limitation of the specific distribution can be nonlinear, so it can be solved by traditional methods. That was the task. The algorithm consists of two stages. The first one involves this limitation of the accessibility distance, and the second one is not. This works very simple. In order to estimate the provisions, it is necessary for each of the services to find the houses in the accessibility zone, according to distance matrix at the right stage. For these houses, we seek for their own services with the same limitation, and then for these services we look for their own houses. So we have this system shown on stage 6, and then we just need to calculate our load vector by giving law of distribution from each house to the each found services and find specific value for the exact services, service 1, which we need to use. And then we just send all these loads to this service. Very simple. If the selected service has more capacity than total demands from all the services he supplied, so it's have nothing more to do. We can also have the situation when the chosen house send all the demands to the particular services, and we just delete him from the distance matrix, and he will never be shown and at the next parts of the algorithms. If the demands are more than capacity of the selected services, this needs some balances, and this is described in article. I won't waste the time for this. At the map, it seems more understandable. So you have a black dot. This is the services. The service. You find all his houses, which he can supply in the selected area with this with the limitations, and you just send all these houses demand to these services. That's it. You just need to balance demand if there are more than one services for one house. And on the second stage, you do literally the same, but with no limitations of range. For example, I should say what is limitations. You can have some government provided normatives for some social infrastructure like kindergartens, so they have to be in the 5 or 10 minutes away from living house. But in the second stage, you doing literally all the same, but you just have no limitations. And if you have no houses with free demands to supply for services, you just try to find closer one with which still have some unsupplied demands. So that's it. Behind the map, we have a few tables, which looks like that. We have a distance matrix based on graph or whatever, with the range or time limits in it. You just need to find with your limitation the services and the houses. Provision tables, which obviously exist zero, so you can say that each house are supplied by each services. Some services with their capacity and capacity left, and some houses with their demands and demands which are left after algorithm assessment. This is a block scheme for a full recursion loop. It can be found in the article with the provided description. And this is a beautiful map of provision assessment. It's have to be noticed that our provision assessments are calculating only for the services and supply demands within the accessibility zone. So you have your map. Even though the houses are red, may be supplied by some services, but just out of the given limitation zone. So that's it.
Thank you. Thank you. Please, questions? Okay. I guess there is no questions. No question.
Я что-то нажал. Так, вот.
Thank you, Alexander. Let's thank the speaker again. Спасибо. And we move to the last talk of today's session. This is a talk of Alexey Rezvых. Alexey, you have 8 minutes. You can start.
Dear colleagues, my name is Alexey Rezvich, and I'm very glad to present to you the results of our study about modeling the workflow of a field hospital in earthquake conditions that we conducted with our colleagues, disaster medical specialists from Kirov Military Medical Academy. Our study lies on the edge of computer science and disaster medicine, which goal is to respond on natural disasters with human casualties and provide medical help to the greatest number of victims. Every year, there are more than 500,000 detectable earthquakes that affect more than 6 million people, approximately 20,000 of which are killed by earthquakes every year. These facts confirm that medical response on such disasters is a critical part of healthcare system of every country. Even more, around 20% of all earthquake casualties require medical help. Our study is dedicated to optimize medical reaction measures determination step in disaster response process. Particularly, how to determine optimal required medical response teams configuration, their amount and complement given disaster parameters. As a base situation to our research, we were given with the data from earthquake contamination training with modeled earthquake in Khabarovsk Krai. To investigate field hospitals' medical teams' workload during earthquake contamination process, we chose discrete time modeling approach. This approach is straightforward, flexible, and does not require real-world training measures. First, we transferred real field hospital structure on modeling abstraction level via computer programming implementation. Then we implement patient's flow logic and conducted a set of discrete time modeling experiments to collect different statistics, such as average queue size, average idle time of all medical teams, average service time. Lastly, we analyzed and visualized these statistics to determine optimal medical teams configuration in different modeling scenarios. Here we can see typical field hospital organization. This scheme can illustrate which processes can be analyzed with simulation approach. In frames of our current research, we focused on patients' flow through medical facilities within field hospital, particularly operational facilities and their complement. We simplified common structure to attain required level of modeling abstraction. We considered only surgical teams workflow. Resulting model structure consists of queue module, where all patients are placed when arrived at field hospital. From the queue, patients arrive to 3 medical teams, and after surgery, they are excluded from the flow. To investigate the workflow of different medical team structures, we compared universal and specialized field hospital configuration models. The main difference between universal and specialized models is that medical response teams in universal model can handle patients with any injury profile. However, each team in specialized field hospital model has its own specialization and is able to handle only patients with corresponding injury profile. We conducted a set of experiments with different incoming flow and field hospital parameters. We considered incoming patients' flow as a Poisson process. In model, we used per minute flow intensity as the main flow parameter, but for results illustration, we used daily flow intensity. The second flow parameter is injury severity distribution over patients, the fraction between lightly, moderately, and severe injured patients. The last flow parameter is injury profile distribution over patients. It defines fractions of 3 the most frequent in earthquake conditions injury profiles: thoracoabdominal, traumatological, and neurosurgical. Field hospital has only 2 parameters. The first is overall number of medical teams. Specialized teams amounts are distributed by profiles according to injury profile distribution over patients, with at least 1 team on each profile. Specialized teams surgery time. It was defined that average surgery time of universal teams is 30 minutes, and for specialized teams, this parameter may vary. One step of simulation process is organized as follows. K patients are generated from Poisson distribution. For each patient in K, we randomly choose injury severity and profile according to their distribution. For universal field hospital, we add patients in common queue, and for specialized field hospital, we add patients to specialist queues respective to their injury profiles. Then, if some team is free or it ends with separation, this team immediately takes the first patient in respective queue. This team will be busy for next TO steps. If queue is empty, 3 teams wait for patients. If all teams are busy, current iteration ends. For every parameter, we defined a set of options: 12 for flow intensity, 1 for injury severity distribution, because during experiments we observed that in current model organization, this parameter does not significantly affect simulation results. 10 options for injury profile distribution. The last one is empirical injury profile distribution. 8 options for team's amount and 11 options for surgery time. To investigate truthfully results, we conducted 30 simulations for every parameters combination with different random number generator setting. Subsequently, results of all 30 runs were averaged to get the final result. Thereby, for universal team field hospital, we conducted almost 3,000 simulations, and for specialized field hospital, we conducted more than 300,000 simulations. Each simulation took 100,000 steps. This heat map depicts the difference between average queue sizes for universal and specialized teams as example results of 88 simulations with daily flow intensity equal to 200 patients per day and empirical injury profile distribution. These heat maps show that for these patients' flow settings, there must be at least 5 medical teams in field hospital because lower amount cannot handle this flow. Moreover, this picture illustrates regions where universal teams are more effective than specialized teams and vice versa. We also collected our results in one dashboard. The user can set incoming flow parameters, daily intensity, and injury profile distribution, and choose the criteria to compare universal and specialized teams. Such criteria as average queue size, average idle time of all teams, or average service time. The link to dashboard you can find on the slide. To sum up, I will highlight that we implemented the simulation model of field hospital workflow and studied vital hospital workload statistics under different patients' flow settings and medical teams configurations. These results were approved by disaster medicine experts, and this approach can be utilized as a part of decision support systems dedicated to manage medical resources and tasks in real time. Our model has the potential to be further modified. We plan to include the irregularity of incoming flow to follow its changes in different time horizon after a disaster. In future work, we also address post-surgical evacuation process and patients' mortality within hospital. Thank you for your attention.
Thank you. Thank you. Any questions? This is the last talk of the session. Yeah, please.
You said that you generated while simulation в общем, пострадавших you generated from Poisson distribution. Why Poisson?
Poisson distribution is one of the most frequently used distribution when simulating patients or customers or users flow in different facilities, and is the most straightforward and close distribution to real life patients flow.
Okay, thank you.
Any other questions? Okay, if there is no more questions, let's thank the speaker again. And I switch to Russian to conclude this session. Forgive me for Russian, but I guess it will be, you can understand me more, it will be more clear. Значит, если я правильно понял, ну я не думаю, что это интересно. Ладно, буду говорить в микрофон, да? Значит, сейчас это надо только писать маркером для белой доски. Вот. Значит, коллеги, я хотел два момента проговорить, благо у нас еще остается чуть-чуть запасик времени. которые, мне кажется, могут быть полезны специалистам, кто занимается вот вопросами, связанными с тем, что сегодня рассказывалось. Значит, первый момент связан с тем, что, вообще говоря, модели агломерационные, вот Urban, всякие модели, вот, например, вам надо восстановить матрицу корреспонденции города, который вот, ну, Санкт-Петербурга, да, вы разбили на районы, и, значит, вот, значит, пускай тут будет n районов, ну и, соответственно, матрица будет выглядеть как d изжитая и g от 1 до n. То есть n в квадрате чисел, вообще говоря. И чтобы брать эти данные откуда-то, ну, вы можете там реально проводить какие-то опросы, это n в квадрате чисел. Чтобы так много данных не требовалось, придумывают всякие модели, типа там гравитационные модели, да, то есть что d изжитое равняется, вот пускай есть какие-то характеристики, значит, районов, сколько здесь рабочих мест, и сколько здесь, извините, сколько здесь мест жительства, и сколько здесь мест рабочих, ну и так для какого-нибудь другого района. То есть каждый район характеризуется парой, сколько здесь мест жительства и сколько рабочих мест. И говорится, что трудовые корреспонденции, сколько людей ездят из этого района в другой на работу, пропорциональные, соответственно, ну как закон Ньютона-Гука, пропорциональны массам района, то есть из района И в район Ж значит, направляется в единицу времени число людей пропорционально массам этих районов. Ну вот если из жилого района И в рабочий район Ж, вот такая корреспонденция, делить на некую функцию, ну, например, квадрат расстояния между районами. И дальше еще два коэффициента вводятся, аитая, бжитая. Эти два коэффициента определяются, соответственно, из условий, что сумма d изжитых должна равняться l итому, если я суммирую по g, и сумма d изжитая по всем и должно равняться w житая. Это условие баланса, что действительно эти корреспонденции отвечают вот этим вот числам. То есть вот набор 2n чисел должен дружить с набором корреспонденции, иначе будет противоречие. Значит, здесь 2n уравнений. Здесь n в квадрате неизвестных. И здесь тоже 2n неизвестных. 2n неизвестных. Мне сложно понять, что, хотя это не то, чтобы совсем просто, потому что это вырожденная система, но тем не менее можно показать, что эти 2n неизвестных однозначно определяются вот из этих 2n уравнений. И замечу, что 2n типично, ну при n, если не очень маленькая, сильно меньше, чем n в квадрате. И вот я хотел сказать, что на самом деле часто для того, чтобы обучать какие-то модели, ну то есть вот это просто пример, модель называется гравитационная, вам как бы выгодно знать, что эти модели есть, потому что вы сокращаете, зачем это нужно? Вы сокращаете размерность объекта, который вы пытаетесь восстановить вот из результатов OpenStreetMaps, еще из чего-то, потому что если вы знаете, что есть какие-то законы, то параметров меньше, это первый момент. Параметров меньше. И замечу, что здесь есть красивейшая математика. На архиве есть, вообще это вот связано с моделями социодинамики, формированием городов, там миграции всякие, ну вот в том числе и модели корреспонденции. Сейчас я, значит, приведу ссылку на архив. Так, 14, 12, 27, 20. То может кому-то будет это полезно. Посмотрите, здесь объясняется математика, которая стоит за такими моделями. То есть как эти модели получаются. Я вот написал, а ничего не доказывал. А хочется понять, почему в жизни они возникают. Почему это, ну, закон Ньютона-Гука, это, вообще говоря, результат экспериментальных наблюдений. А нам бы хотелось, ну, является следствием того, что вот такая гипотеза, что две массы притягиваются обратно пропорционально квадратам. Значит, доказывается это просто результатами наблюдений. То есть, если бы было не так, то мы бы не видели периодических орбит там вот таким образом. Здесь немножко другая философия, что здесь просто делаются разные предположения о том, чем люди мотивируются, когда формируют там город, когда город растет. И эта математика приводит к неким аттракторам, и эти аттракторы изучаются. То есть это есть результат как бы стабилизации некой системы. Это первая идея, которая позволяет, значит, существенно упрощать размерные задачи. Второй момент, на который мне хотелось обратить внимание, последний, что когда вы проводите опросы, то важен выбор метрики. Вот вы, например, матрицу корреспонденции пытаетесь определить, и возникает вопрос, вообще общий вопрос. Вот если вам надо, прошел какой-нибудь второй тур выборов, и вам надо определить, кто из кандидатов победил, то сколько человек просить на выходе с избирательного участка, чтобы сказать, что победил А, с точностью там 1% и с доверительным уровнем 99, с вероятностью 0,99. Ответ где-то 6 тысяч человек. Этот результат получается, ну, то есть, если вы 6 тысяч человек опросите независимо, то вы можете более-менее точно сказать, кто победил. А если мне не 2 кандидата, а вот n в квадрате кандидатов, ну, то есть мне надо восстановить матрицу корреспонденции из опросов населения или как-то еще. То есть у меня не 2 числа, по сути, связанных между собой, до 1 доля, ну, там, не знаю, 45% за, 55 за b. То есть если я знаю 45, 55 я определю. А тут у меня вон много чисел. Это что, значит, надо брать не 6 тысяч, а намного больше? И вот в этом месте возникает такой хитрый момент. А что вы хотите? Как вы хотите восстановить d? Вот если вы хотите восстановить d, оценка d минус d со звездой настоящая в 2 норме меньше, чем тот же 1%, то вам те же 6 тысяч будет достаточно. Ну, там по порядку. То есть, если вы берете метрику, просто 2 норма разности векторов, то размерность вектора практически никак не влияет на то, сколько человек надо просить. Но если вы хотите каждую компоненту, так сказать, оценить с нужной относительной точностью, то есть сама d маленькая, и вы хотите, значит, соответственно, с относительной точностью, вот тут будет проблема. Вот тут уже будет как бы все плохо. Но повторю, что вот вопрос, собственно, в том, что вам нужно. И часто бывает этого достаточно. Почему? Потому что если d маленькая, то относительная точность высокая его определения вам и не нужна. Ну какая разница здесь? И так мало, это в целом мало влияет на систему. Я вот этот второй момент, на который хотел обратить внимание. То есть когда мы проговариваем скороговоркой, что мы восстанавливаем что-то, то вопрос, как именно, потому что это векторные данные. В какой метрике вы восстанавливаете, аппроксимируете один вектор другим? И от этого, значит, много чего зависит. Вот. Ну, хорошо. Ну, например, есть один метрика. Вот. Почему, как это получить? И вообще вот эти результаты. Это такие интересная наука, неравенство концентрации меры, всякие, так сказать, современная статистика. Это, к слову, о курсе математика больших данных. Там все это будет. Ладно, извините, все, хватит рекламы. Все, в принципе, надо заканчивать сессию. Мы по времени уложились. Вот мне оставили время, я немножко похулиганил. Все, спасибо, коллеги. До свидания. Да.
So that's it for YouTube today. We'll see you tomorrow at 10 a.m. Moscow. We'll start with Alexander Bukhanovsky lecture. Don't miss it out. Thank you for your attention. Bye.